All right, so we've taken the time to develop some nice rules to avoid cumbersome computations when taking derivatives. If you've got a sum of two functions, the derivative works very nicely. Take the derivative of the two things, sum them together. The derivative of a difference works similarly nicely. Derivative of a product was somewhat cumbersome, but hey, it's doable and that's kind of cool. Derivative of a quotient came out kind of clunky looking, but again, this formula works, so anytime you've got a function which is a quotient of two functions, you now have the ability to compute the derivative. Kind of cool. Here we're going to look at a scenario which is maybe somewhat different than these other scenarios. In a sense, we're looking at not where we have a sum of two functions, but where we have a sum of a constant times a function. Here, note, C is just some real number. So C could be 5, C could be 10, C could be minus 2, C could be 7.5. So what would a function look like of this form if you were imagining? What if you had a function that wasn't, say, x squared, but was 5x squared? Because you see, well, here's a perfectly valid function, right? Plug in something for x, you get something out. Plug in x equals 2, you get out 4 times 5. Plug in x equals 3, you get out 9 times 5. Plug in x equals 5, you get out 25 times 5. Plug in whatever you want for x, you'll get out whatever x squared is times 5. So here's a situation where you have a function which is an expression involving x times just a number. And that's exactly what we're saying here. We've got a function which is some expression involving x times just a number. And we want to compute the derivative of that. And like we've done to this point, we're going to produce the evidence for such, and then after producing the evidence, we will have a hard and fast rule which will allow us to compute the derivative every time. So, well, how are you going to compute the derivative of this? Like you always can do, go back to the definition of the derivative, but the beauty of going through this evidence is we will do this together once, you'll never have to do it on your own, and once we've gone through it, the rule will ultimately guide us as we go through any examples henceforth. So let's get the evidence out of the way so we know what our goal statement looks like. So let's take the derivative of a constant times a function. So like any derivative always is, you take the limit as h approaches 0 of your original function, plugging in x plus h, that would be constant times f of x plus h, minus the original function plugging in x, that's constant times f of x, and this is over h. Standard formula for the derivative. Plug in x plus h, plug in x, subtract, put over h. And now as you look at this guy, note both terms in the numerator have a c in common, so we can factor out that c, and what will be left is just f of x plus h minus f of x over h. And even as I said that, f of x plus h minus f of x over h, you know what that is. That is the derivative of f. So whenever you take the limit here, you're going to get c times the derivative of f. And note here, actually, as I write this, this fully accounts for our limit. Because c does not depend on h, c is just a number. Whether h is 10 or 20 or 50 or whatever h is, c is just c. So c is actually not affected by h approaching 0, and the only thing where h is affected is this expression for the derivative. So we've got it. The derivative of a constant times a function is just the constant times the derivative of that function. And we can sort of like relax in some sense, because amid the process of computing these very cumbersome rules for a product of two functions and a quotient of two functions, we now have a rule for a constant times a function that works out very nicely. So the long story short, when you take the derivative of a constant times a function, the constant goes through unaffected, and only the part involving x you have to take the derivative of. So whenever you look at 5 times x squared, this our constant times our function. When you take the derivative, it's the constant times the derivative of that function, which in this case is what? Well, our constant was 5, And f prime is the derivative of x squared, which is 2x. So our derivative here is 5 times 2x. Our derivative is, simplify, 10x, right? Because 5 times 2 is 10. 5 times 2 times x would be 10 times x. And if our original function is 5 times x squared, its derivative is 5 times whatever the derivative of x squared is. That turns out, in simplified form, 10x from the 5 times 2x. But here's the long story short, guys. Anytime you got a constant times a function, you can take the derivative by the constant being unaffected and the part involving x taking its derivative.